Section 4.2, the mean value theorem, or MVT. You can write MVT on the AP exam, and they will understand that it is the mean value theorem. Okay, so before we go over the mean value theorem, we need to review the intermediate value theorem, which you can use IVT to represent the intermediate value theorem. And again, you can use that on the AP exam. The intermediate value theorem says if a function f of x is continuous on the closed interval from a up to b, then for all y values between f of a and f of b, the corresponding y values, then there exists at least one number x between a and b in the open interval between a and b, such that f of c equals that y value. So in this case here, we started off at the point a comma f of a, we ended up at b comma f of b, and it's basically saying that it passes through every single y value at least once. So in this case, it passed through m 3 different times, but it could be once, it could be twice, it could be as many times as you want. So if I have this example instead, then it just goes through it once, and so there's a value c, this one right here is our c, between a and b, such that f of c equals that y value. So in this case, we're calling that y value n. The mean value theorem is very similar, only this deals with slopes. The intermediate value theorem deals with y values, mean value theorem is slope. And also there are two hypotheses to the mean value theorem. Mean value theorem starts off just like the intermediate value theorem, where the function has to be continuous on the closed interval a to b. But you have a second thing, which says that the first derivative has to exist on the open interval a to b. Right? Because it deals with derivatives and slopes, well, that means that the slope needs to exist everywhere. And we make it a soft bracket instead of a hard bracket, because it doesn't matter what the slope is. Let's say that there are endpoints here and here. Okay, it's continuous on the closed interval, right? Because we define continuity of endpoints, that the function is exactly what the limit is from the right for a left endpoint. Here, the function is exactly what the limit is from the left. So therefore, it's continuous at a and b, but the derivative doesn't exist at a and b. So since we don't care about that, then we just leave out the a and b. So the conclusion to this, if we know that the function is continuous and that the slope exists everywhere, our conclusion is that there's at least one number c between a and b, just like before, c value or x value between a and b, such that the slope at c on your function, so your slope of your tangent line, is equal to f of b minus f of a over b minus a, which is your average rate of change, which is slope of a line, which is the slope of the secant line. So here, you can see this is your secant line that goes between a f of a and b f of b. So the slope of this is the right-hand side of this equation. It's just your change in y over change in x. And on your left-hand side, you have the slope of the tangent line. So at c, right, here's your function, black function up here. At c, this is what your tangent line would look like. And you can see that the slope of that tangent line is the same thing as the slope of our secant line. So these two lines are parallel. This is the place where slope of your tangent line equals the slope of your secant line. Here's another picture. We start here at A, and then we end up here at B. And here is our secant line. And there are two different places, here and about here, where the slope of your tangent line is the same thing as the secant line. This first picture, you just have one C between A and B, where the slope of the tangent line is equal to the secant line. Here you have two different places. And this kind of makes sense because let's say this one, let's say here your slope is 1/2. Well, here your slope starts off very positive, so it's already bigger than 1/2, and then it gets smaller and smaller. So here it's going to 0, and then it's getting negative, negative. Well, at some point between really positive and somewhat negative, you're going to have to go through a slope of 1/2. So it's very similar to the intermediate value theorem, only now we're talking about slope, like I said before. Same thing over here. Let's say that this is a slope of 1. Well, this is really positive, and then it turns to negative, so it must have passed through a slope of 1 at one point. Um, and then here it was really negative, and then it was turning to really positive, so again, it must have a slope of 1 at some point in there. So let's do some examples. So part A says we're going to say whether or not it satisfies the two hypotheses of the mean value theorem, and then part B is we're going to find the value of C on that interval that satisfies this equation, which is directly from our mean value theorem. So first of all, from our function, we can see, yes, that is a polynomial, so therefore it's continuous and differentiable everywhere. So clearly it's continuous and differentiable on that interval. So let's just write this down. Yes. The mean value theorem holds since f of x is a polynomial which is continuous and differentiable on all real numbers. Right, there's no denominator to ever be 0. There's no square root. And so there's no places where this function can be undefined. Also, there's no place where the derivative to be undefined because your derivative is also a polynomial. Very good sentence. Okay. For part B, we actually need to find the value of C between 0 and 1 such that the slope of the function at C is the same thing as f of 1 minus f of 0 divided by 1 minus 0. So we're going to find the C value, so I'll just use x. And so therefore I'm going to find the derivative. So the derivative of x cubed minus 2x plus 1 is 3x squared minus 2. We'll solve for the x value, or in other words, C value. And that has to equal f of 1. So let me write this out so it doesn't confuse you. Minus f of 0. It's just the definition of slope. Over 1 minus 0. Okay. And then I'm just going to plug this in and then solve for x. So f of 1, I get 1 cubed, which is 1, minus 2 times 1, it's just 2, plus 1, minus all of 0 cubed is 0, minus 2 times 0 is 0, plus 1, so minus 1, all over 1. 1 minus 1 cancels. 1 minus 2 is negative 1. Negative 1 over 1 is negative 1. Okay, I'm going to solve for x. I put everything else on the other side. 3x squared, add 2, get 1. X squared equals 1/3. Therefore, x equals plus or minus square root of 3. Okay, so it looks like there's two different places where the slope of the line tangent to this function is the same as the slope of the secant line, right? So the slope of the secant line is the right-hand side of the equation, which is -1. So the slope, if I was to graph this function, and I had a point at 0 and a point at 1, well, then the slope of the line that passes through those 2 points would be -1. And at 2 different x values, then this function has the slope of the tangent of -1. And only one of these is in the interval 0 to 1, and obviously that's the positive value. So x equals positive square root of 3 over 3. That's it. So f prime at square root of 3 over 3 equals -1, and also the slope of this function between 0 and 1 is -1. All right, next page. F of x equals log of 2x plus 4. So here we need to make sure that the function is actually continuous there, right? Because we cannot take a log of a negative number. We need to make sure that whatever we're plugging in here is positive. So this is continuous, and if whatever we're taking the log of is positive, and if I was to solve, 2x is greater than -4, x is greater than -2. Okay, good. So that means that my function at a vertical asymptote at -2, I stretched it, but that doesn't matter because it doesn't affect the domain at all. So my function looks something like this, right? It only exists when x is greater than -2. And we only care about 0 to 3, so therefore it is going to work. Okay? And my slope is going to exist everywhere, so I'm absolutely fine. Right? If I had anything that was either equal to -2 or less than -2 included in this interval whatsoever, then the mean value theorem would not hold. So yes, this holds. Yes, f of x is continuous. Closed interval 0 to 3, and differentiable open interval 0 to 3. Of course, you could just say both of these on x is greater than -2, or soft bracket -2 to infinity. So the mean value theorem holds. Okay, now we just need to find the c value. So we set the derivative equal to the slope of the secant line. So derivative log of this is 1 over 2 plus 4 2 equals, if I plug in 3, I get log of 10 minus log. Plug in 0, you get 4 over 3 minus 0. 2 over 2x plus 4 is 1 over x plus 2. Log of 10 is 1. Now we just need to cross multiply. So we get 3 equals, multiplying both by 1, I get x plus 1. Multiplying both by negative log of 4, and I get negative x log of 4 minus 2 log of 4. And since I want to solve for x, then I factor it out. So with these two terms, right? So I'm going to put these two on the right-hand side. 3 minus 2 is 1. And then add this to log 4 plus 1. And x equals 2 log of 4 minus 1 over 1 minus log of 4. And if you put that in your calculator, and it's between 0 and 3, then you're almost. Okay, last question. This one, you can already kind of see that it's probably not going to work, right? We want it on the interval 0 to pi. Well, first of all, we need to make sure that the two hypotheses hold, which is that the function needs to be continuous and it needs to be differentiable. Well, even if it's continuous, even if they meet up with each other, they never meet and have the same slope, right? So first, let's at least make sure that it's continuous. Think about the graphs of the original functions or think about your unit circle. Either way, we need to check and make sure, right? This is a piecewise function between 0 and pi over 2. This is between pi over 2 and pi. So we need to make sure at pi over 2 that they're actually meeting up with each other. And they don't, right? This is 0, 1. So therefore, cosine of pi over 2 is 0, and sine of pi over 2 is 1. So therefore, this is not a continuous function. So therefore, the mean value theorem cannot hold. So let's say that. Since we need to say why it is not continuous. So since limit x goes to pi over 2 from the left, right, because 0 to pi over 2 is to the left of my function equals cosine pi over 2. Right, this is from the left because 0 to pi over 2 is to the left of pi over 2. So we plug it into the cosine function, cosine of pi over 2, which was 0, let me put here, which is not equal to limit as x goes to pi over 2 right. And then we're looking at this side, pi over 2 to the right. So I plug it into my sine function. Sine of pi over 2 equals 1. So since this is not equal to this, f of x is not continuous. H equals 0 to pi. Closed interval. So, mean value theorem does not. Now that doesn't mean that there isn't a place where the secant line has the same slope as the tangent line somewhere on the interval 0 to pi, but this mean value theorem ensures that you have to have at least one place, and therefore that is not happening here, right? Maybe there is still one, but we're not guaranteed one. And here's your homework.